Good afternoon. So let us continue with continue where we left off last week. So basically, last week we provided you with some information regarding the stress tensor. We talked about how this stress tensor is actually going to be used in order to predict failure at a particular point in an arbitrary loaded material, right? An arbitrary loaded component or a member, so to speak. So what we said was there is some function which is basically a function of the principal stresses at a particular point, and we said that whenever this particular function reaches a certain critical number, the material will fail. Okay, and we defined failure as several things. So firstly we were talking about failure as yielding, which is what is important to us, especially when it comes to ductile materials. So we developed this function for a ductile material, and we called it the von Mises criterion, or the distortion energy criterion. So what does that criterion say? It says that whenever the strain energy density only because of the distortion component of the stress tensor reaches a certain critical value, the particular point in the material could be considered as yielded or failed. So if you take a look at slide number 21, okay, it talks about a particular equation number 34. It says that whenever this expression whenever this expression is satisfied, then we say that the particular that particular point has yielded or failed. So if you take a particular member, it is arbitrarily loaded, it is fixed at some particular point, it develops stresses throughout the domain. Okay, at every particular point of the particular at every particular point of the domain, you are supposed to calculate this particular quantity. Okay, for given loading, sigma 1, sigma 2, sigma 3 will all depend upon the loading and the geometry only, right? It will develop some sort of you will be able to calculate this function. Then you will see if that numerical value is equal to sigma y or not. If it is equal to sigma y and greater than that, you will conclude that this particular point has failed. Okay, it has failed. Of course, failure need not necessarily mean that it needs to break, right? We could think of plastic deformation or yielding at a particular point also has failure. So sigma y is the uniaxial yield strength of the material, and that is how you have to perform a uniaxial tensile test in order to come up with this criteria. Otherwise, you only get the maximum energy that is stored in the material. In order to say what the critical value is, you need to perform the uniaxial tensile test. So this is a criteria that is generally used for ductile materials like copper and steel, etc. And experiments have shown that it is quite accurate. Okay, especially for metals. And primarily, it is true. It is good for metals because it, as far as metals is as far as metals are concerned, the deformation or yielding basically happens because of a slip mechanism, like what we talked in the last class, and distortion energy density, or the amount the stresses that are responsible for basically changing the shape of the infinitesimal volume element are more responsible for actually causing the dislocations to move. The hydrostatic stress components will not do anything to the dislocation, it will just stay there. Okay, so this is as far as von Mises criteria or distortion energy criteria is concerned. Other criteria are also used for quick back of the envelope calculations. However, depending upon the material, some of the materials might show a good might agree well with the Tresca criterion, while others might agree well with the von Mises criterion. One would actually have to do a experiment to figure out which of these criteria is actually a good one. Okay, as far as Tresca criterion, or the maximum shear stress criterion, what it says is that whenever the maximum shear stress. So I am going to use the symbol tau to represent the shear stress. Whenever the maximum shear stress reaches a critical value, the material fails or yields, either ways. Okay. So what is this maximum shear stress that you are going to see? So you must have studied from strength of materials that you can represent the state of stress at a point using Mohr circle. So what does a Mohr circle tell you? You basically draw the normal stresses in the x-axis, the shear stresses in the y-axis. Okay, at any given arbitrary plane, you are able to mark the corresponding value of stresses, and then you are able to draw the Mohr circle. I don't want to go into the construction of a Mohr circle. I'm sure you all have studied it in your mechanics of material class, and you remember it quite well. It so happens that you get a circle, and the circle basically will intersect the normal value at 2 points. So let us call it, say, sigma 1 and sigma 2 for for the purpose of this class. These particular values of stresses are called as the principal stresses. Okay, of course, if you don't want to do a Mohr circle, you could also use the method that I talked about in the first class of finding the characteristic equation to find out the principal stresses. But for 2D, it is quite simple. You all must be remembering a simple formula in order to calculate these principal stresses. So once you know the values of the principal stresses, you can calculate the maximum value of the shear stresses as being the radius of the circle, which is essentially sigma 2 minus sigma 1 divided by 2, the modulus of it, because the sign of the shear stress really doesn't matter. Okay, so what you have to do is you essentially have to calculate this maximum shear stress, and you have to say the critical value, right? Whenever this reaches a critical value, you are saying that it is failing. So how do you find out the critical value? You have to do again a uniaxial tensile test experiment, perform a uniaxial tensile test experiment. Okay, keep loading it until say, let us assume that this is the one direction. Okay, let us assume that one direction. So in this state of loading, the only state of stress is sigma 1 is equal to, say, P by A. This is the this is the cross section area A. Okay, so as you keep loading it, the stresses are increasing. Okay, and sigma 1 increases at a particular value of sigma 1 equal to Sy. You see that the material is yielding, right? Material is yielding. But how will you fix the critical value of the maximum shear stress? So if you draw the Mohr circle at yielding for the uniaxial experiment, you get the following, right? Sorry, it won't go like this. You will get something like this. This would be equal to Sy. This would be equal to 0 because there is no stress component in the other direction, in the two direction. Only in the one direction you have stress, and at yielding it is equal to Sy. So the maximum shear stress at yielding would essentially be equal to tau max at yielding modulus of Sy minus 0 divided by 2. 0 is the second other principal stress. So you get this is equal to Sy divided by 2. Okay, since Sy is basically positive, there is no point in having all these things. So Sy divided by 2. So what Tresca criterion tells is whenever tau max, which is basically the response of the material to the loading, okay, which is a measure of the response of the material to the loading. The resistance to deformation is kind of captured by this. Whenever this parameter at every point in the member, you compare it to Sy by 2. Whenever this condition is satisfied, you decide that the material is failing. Okay, that is what is called as the maximum shear stress criteria. Of course, there are a couple of different conditions, and the geometry taken by both the von Mises stress criterion as well as the Tresca yield criterion is kind of interesting. We will take a very brief look at that in the next slide. So if you take a look at slide number 23 of 37, it shows you a slide which is titled Geometry of von Mises and Tresca criterion. I'm sorry, it says Trees criterion there, but it's supposed to be Tresca criterion. That's a typo there. So this particular way of representing the failure envelope is quite useful in visualizing, how what are the regions or combinations of principal stresses which actually keep the material safe, and what are the values, whenever the values of sigma 1, sigma 2, sigma 3 lie on the surface or outside of this particular surface, you consider the material to be yielding. So as far as Tresca criterion is yield, as far as von Mises criterion is concerned, this particular expression that you wrote, sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square is equal to 2 sigma y square. This condition, so if you take this as the x axis, this as y, and this as z, okay, in Cartesian space, and if you plot this particular function, it will also happen to be a cylinder. Okay, it will also happen to be a cylinder which has its axis in a direction which makes equal angles with the x, which is basically here the sigma 1, sigma 2 and the sigma 3 axis. So it's basically a cylinder, which looks something like that. Of course, it's I can't draw it very well because it's a three-dimensional thing. However, this particular axis makes equal angles with sigma 1, sigma 2 and sigma 3. Okay, so suppose we take any arbitrary and going anywhere along the radius of the cylinder, if you the second you touch the surface of the cylinder, you have basically reached a combination of sigma 1, sigma 2 and sigma 3 which is going to cause yielding in the material. Crossing this, of course, is again yielding, but other things will happen. Like I told you, we will not look at post yield behavior. Within this radius, you are always within the elastic limit. The combination of sigma 1, sigma 2, sigma 3 which keep you inside the cylinder essentially means you are safe, you are not yielding. Now another interesting thing is, suppose you have an arbitrary value of sigma 1, sigma 2, sigma 3. Okay, sigma 1, sigma 2, sigma 3, an arbitrary value is taken. What happens if you take the projection of the sigma 1, sigma 2, sigma 3 right on this axis? So let us take this axis. This axis is, it makes equal angles with x, y and z. So I am going to call this as a normal axis, and this normal axis is 1 by square root of 3i plus 1 by square root of 3j plus 1 by square root of 3k is the vector which is pointing like that, in such a way that it is making equal angles with sigma 1, sigma 2, sigma 3 axis. Now this particular vector right here, sigma 1, sigma 2, sigma 3, okay, this particular point in the principal stress space is nothing but sigma 1i plus sigma 2j plus sigma 3k. Okay, what happens to the projection of this point OP onto the hydrostatic, onto the normal, onto this particular the axis of the cylinder? So if you want to do that, you just have to take the dot product of this and this. So you get OP vector dotted with n vector, you will get something like sigma 1 plus sigma 2 plus sigma 3 divided by square root of 3, right? What is sigma 1 plus sigma 2 plus sigma 3? Is nothing but 3 times the hydrostatic stress divided by square root of 3, which is nothing but, say, square root of 3 times the hydrostatic stress. Okay, so interestingly, this is just a scale factor. All that I have shown you here is that if you start walking along the axis of the cylinder, you are basically exploring different values of the hydrostatic stress, right? You are exploring different values of the hydrostatic stress, right? At any value, you sit there and you start walking towards this particular value. The value of the radius of the cylinder at which you basically yield is essentially going to be the same, correct? This also very nicely captures the essence of von Mises criterion. Remember what we did when we started off deriving the von Mises criterion? We subtracted out the energy that is associated with the hydrostatic component and we took into account only the deviatory component, right? It's distortion energy density which is important as far as your von Mises criterion is concerned. This kind of geometry captures the essence that, no matter what the value of the hydrostatic stress is, the value at which you yield will essentially be the same, is what this particular geometry is telling you. So this is I'm not sure whether this is there in your syllabus at this point, but it is a very useful way of understanding yield criteria, and this is very commonly followed and used to explain some of the complicated results, and other criteria also have similar representations, which we will not go into. Now the other criteria is the Tresca criterion. As far as Tresca criterion is concerned, it so happens that it is a hexagon. I mean, my drawing is not so good, but you can take a look at this picture which I got from Wikipedia. Okay, they have a very nice picture showing you the hexagon, which tells you what the envelope, okay, the failure envelope looks like in three-dimensional principal stress space, and any point outside this hexagon again would mean failing, and any point inside it means that you are in the elastic regime. Okay, so now let's come to something that you might all be familiar with a little bit, right? You might all be familiar with the failure criterion, Tresca failure criterion in 2 dimensions. So that is how it looks. So let us come to that. This is something important. Maybe the 3-dimensional version was not really a part of your syllabus or something like that, but the 2D is very important. So what happens if one of the principal stress is 0? If you take this hexagon, okay, hexagonal pyramid, which basically is having its axis parallel, having its axis, in such a way that it is making equal angles with sigma 1, sigma 2 and sigma 3 axis. Now you take a plane and cut it in such a way that one of the principal stresses is 0, say sigma 3 is 0. So now we are trying to understand the geometrical interpretation of the Tresca criterion. Okay, so as far as the Tresca criterion is concerned, we saw that in the Hay-Westergaard or the principal stress space, the Tresca criterion was basically a hexagon, right? A hexagonal base pyramid. Now if I take, say, sigma 3 equal to 0, if I take a sheet and cut it at sigma 3 equal to 0 and have only a two-dimensional or two principal stresses to worry about, then the hexagon basically becomes a little bit distorted and you have something like this as the criteria for yielding. So anywhere within this distorted hexagon, you would essentially be elastic, you would be safe. So as you start loading the material from here, okay, for this particular combination of sigma 1 and sigma 2, you would basically be safe, it would be still in the elastic regime, and you continue loading, you would reach this particular line, and because it satisfies the, it is touching satisfying the criteria for yielding, you would consider that this combination of sigma 1 and sigma 2 are basically going to fail the material or yield the material as per Tresca criterion. Now let us see how these things come about. I haven't marked all the regions here, but it is not very difficult to see. So let us first consider a situation. So we are talking about only two stresses, only two components of principal stresses, sigma 1 and sigma 2. Let us take the case of, let us take the Mohr circle to be as follows. Let us take a state of stress such that this is the Mohr circle, okay. This happens to be, say, sigma 2, this happens to be, say, sigma 1, which is equal to 0, right. Now under this condition, let us see what is the maximum value of the shear stress. Sigma 2 minus sigma 1 by 2 must be equal to Sy by 2. Sy is the uniaxial yield strength of the material. So this means sigma 2 by 2 must be equal to Sy by 2. We remove the modulus and put a plus or minus there. So therefore this implies sigma 2 is equal to plus or minus Sy. So when sigma 1 is basically 0, then you get sigma 2 is equal to either plus Sy or minus Sy. In a similar spirit, you can have a state of stress where the situation is something like this. This is the Mohr circle, right? Now this is say sigma 1 and this is sigma 2, okay. For this Mohr circle, if you happen to write the Tresca criterion, you would get modulus of sigma 1 minus sigma 2 by 2 is equal to Sy by 2, and this tells you since this is 0, you get sigma 1 is equal to plus or minus Sy. So when sigma 2 is 0, you either get sigma 1 is equal to plus Sy, sigma 1 is equal to minus Sy and plus Sy, right. So therefore this particular value is Sy, Sy is. So you marked, you know how these lines came? You know how these lines came? These lines come because of the fact that one of the principal stresses was essentially 0. For the shear stresses, you need only the maximum minus the minimum. Since the minimum was 0, only this was important in fixing the criteria. Now you can have another situation which looks something like this. You can have another situation which looks something like this, where you have this as sigma 1 and this as sigma 2, this as the origin, right. Now in this case, the maximum shear stress modulus of sigma 1 minus sigma 2 divided by 2 must be equal to Sy by 2 for yielding, right, for yielding or failure, whatever you want to call it. So when this is the case, you get sigma 1 minus sigma 2 is equal to plus or minus Sy. Okay. What is this? This is the equation of the line, either it is equation of this line or equation of this line. So these two basically represents this is how actually the Tresca criterion, the geometrical interpretation of Tresca criterion comes about. When you look at 2-dimensional, of course in 3-dimension, if you take all combination of sigma 1, sigma 2 and sigma 3 and try to come out with the failure envelope, it would be a regular hexagonal pyramid with its axis making equal angles with sigma 1, sigma 2 and sigma 3 axis. Now why that is the case and what is the proof of that, you can do it using mathematics, but we don't want all that. I just wanted to, as far as the geometry is concerned, in case people did not follow as to because I was going a little bit faster. The only thing that I wanted to point out there was when you had that criterion, this is the von Mises cylinder. This cylinder is basically the surface, right, represented by the von Mises equation. What I wanted to point out is that as you walked along the hydrostatic axis and went about the radius, it always yields at the same distance, and this nicely captures your von Mises criteria, which itself was derived from the fundamental assumption that the hydrostatic stress or the hydrostatic energy does not contribute to yielding. Okay, so that is the reason why I wanted to point this out. There's nothing more. Now what happens if you have the von Mises criterion, but now you are once again making one of the principal stresses 0, right? You're not looking at a cylinder. Now what are you looking at then? If you look at it in 2D. So in Tresca criterion, it looks something like this. It looks something like this. For von Mises cylinder, if you take that cylinder and make a section at say sigma 3 is equal to 0 approximately, you would land up with an ellipse that is in such a way that the Tresca criterion is present inside it. Okay, these values still continue to be Sy, minus Sy and minus Sy. Okay, so I think I have a picture of it. You can take a look at. Oh no, I don't have a picture. I don't have a picture of it, but this is how it is going to look. Now, if you are here, okay, and you keep walking, or if you have a state of stress somewhere inside this domain, okay, inside this domain which is marked with dashed lines, or the domain that's marked with the thick lines. Either ways, if you are inside this domain, you could consider that the state of stress is elastic. Okay, it is elastic and it is not going to fail the material. But according to the Tresca criterion, if you hit this, you fail. Whereas according to the von Mises criterion, you have to go a little bit further in order to say that the material has failed. Of course, which one of these two is true depends upon the material, and you will have to perform experiments in order to figure that out. But nonetheless, failure can be defined either with this or with this. But suppose when we are trying to design a particular component, we decide to use the Tresca criterion. Okay, then the combination of sigma 1 and sigma 2 at which we reach the failure point will essentially be much more quicker when compared to the combination of sigma 1 prime and sigma 2 prime, for which we reach the von Mises failure envelope. Correct? So what that essentially means is that the Tresca criterion is more conservative than von Mises. Or von Mises criterion. So it would be more safer to use Tresca criterion than the von Mises criterion. But because people have done a lot of experiments, people feel that the von Mises criterion can actually actually does a good job when it tries to identify failure in real metals, for example. Okay. Now we have completed ductile materials. As far as ductile materials is concerned, we had the Tresca criterion and the von Mises or the distortion energy density criterion, distortion energy criterion. Now we go into brittle materials. So one of the most important thing as far as these failure theories is concerned is fact that you need to know at least approximately whether the material is actually brittle or ductile, right? So you might have taken steel, you might have done a lot of heat treatment and it might have become brittle and it's not ductile anymore. Okay, so that sort of information must be available to you, and you should apply the right criteria for the right kind of material. Okay, if you apply ductile failure criteria for a brittle material, it won't work, and neither will it work the other way. So there is some difference in the underlying principles which actually govern the failure of the material. So we saw failure or yielding. Okay, so as far as brittle material is concerned, we saw that if you took a ductile material and plotted its stress strain graph, it looks something like this, right? It has a substantial long region where it can be plastically deformed. It can take that plastic deformation or permanent deformation to a large extent, and this is primarily possible because of the presence of dislocations which can slip. The greater the number of dislocations and the greater the possibility for these dislocations to move, the greater is the ability of the material to yield. Okay, and this behaves like a ductile material, and this is a ductile material. If you take brittle material, the stress strain response will look something like this. Stresses increase, and then there will be a sudden drop at a particular point. No, it depends. Okay, it will just stop. But this is a straight line. Okay, this is a straight line. Although I have not drawn it like that, this is a straight line. It will fail. It will not show any permanent deformation. It will be very small. The permanent deformation will be so small it is almost negligible. Okay, and this value is called as the ultimate tensile strength of the material if you perform a uniaxial tensile strength. So now, what are the differences in the mechanisms that are acting in this material and this material, in ductile material and then the brittle material? In a ductile material, we saw that the dislocations slipped in slip planes, okay, and because of which you are able to pull this material to a large extent. In brittle materials, nothing like that happens. As you keep deforming the material, a lot of elastic energy gets stored. When the stresses reaches a critical value, the bonds break and the material fails. But actually, it's not the bonds which are breaking in a. When I say bonds break, that means I'm assuming that the material has no flaws, right? But that is not the case. In real materials, there are very small microscopic flaws which are distributed uniformly in the material. So these flaws actually open up. Okay, so if you have a material and there are a large number of small flaws distributed throughout the material, and if you subject it to some load, then some of these flaws or cracks can basically open up, right? So it is because of the fact that these cracks open that the material fails. There's some small crack growth, and all these cracks will basically coalesce or meet together, and finally they will result in failure of this particular component. It will break. The component will catastrophically break without showing any significant plastic deformation. That is the brittle material. That is as far as your brittle material is concerned. Cast iron is a very good example of brittle material. Because of the heat treatment process, it develops a large number of minute flaws in the entire domain. Okay. So that difference, what does this difference mean? What does this difference mean? As far as ductile materials is concerned, we saw that if you take this material, it's large number of dislocations. So this T that I am drawing here is some dislocation. Okay, some dislocation. You take this material, and if you subject it to hydrostatic stresses, compressive or tensile. So either the state of stress is like this, compressive or pulling on both sides. Okay, either ways the dislocations don't move. Correct? The dislocations don't move. Whereas if you had the brittle material, so this is a small point here. This is a small point. Whereas in the case of brittle materials, you have a large number of flaws, right? Take a small element. So this is the flaw in that particular small element. This is the flaw. Okay. Now I am subjecting it to tensile hydrostatic stress. When I subject to tensile hydrostatic stress, what will happen? The cracks will open, right? So, and when I subject it to tensile hydrostatic stress, compression, whatever cracks are open, if there is open crack, that crack is going to close. So, unlike the criterion for the ductile material, which was independent of the hydrostatic component of the stress, for the brittle material, there is no such constraint. If you have different values of hydrostatic stresses can cause failure of the material at different instances of time, at different values of the at different values. Okay, so it is not independent of the failure is basically dependent on the hydrostatic stress, unlike what it was for the ductile material. Okay, so this dependence can be captured also nicely in a geometrical manner. As you can imagine, it will look more like a cone, right? It will look more like a cone. So if you have the what will happen is, suppose sigma 1, sigma 2 and sigma 3 are all negative. Okay, I have just drawn the negative. Okay, it's subjected to a large compressive hydrostatic stress. When it is subject to a large compressive hydrostatic stress, and along with that stress, if you try to perform a tensile test on it, it will fail at much larger values of this radius, okay, than when you take it to more tensile regions. So you subject it to tensile X, tensile Y, tensile Z, take it like that and then perform a tensile experiment, it will fail even more at a lower value of the stress, isn't it? So for such materials, the brittle materials, the geometrical interpretation looks something like this. Okay, it will be large in the compressive hydrostatic stress and it's really small in the tensile hydrostatic region. Now, what criteria can we use for brittle materials? So this is very general, right? It looks like a cone. I didn't talk about the equation of a cone and all that. So let us look at some simpler theories which govern the failure of brittle material. The first criterion is called as the Rankine criterion, and or the normal stress criterion. Normal stress, maximum normal stress criterion. Okay. Whenever, so there are at every particular point, you all know how you calculate the principal stresses. at any one particular point, you see each of these three components. Whenever the maximum component, okay, reaches a certain critical value, you say that the material has failed. Okay, that is called as the Rankine theory or normal stress theory. So if you want to talk about the geometrical interpretation of the Rankine theory, it says that whenever sigma 1 or sigma 2 or sigma 3 is equal to some sigma ut, ultimate strength of the material, that particular point is considered to have failed or opened up. Okay. So if you take, each of these can be taken. So you get a plane here, you get a plane here, and you get a plane. So you basically get a cube in the three-dimensional sigma 1, sigma 2, sigma 3 space. And if you make one of the things as 0, sigma 3 is 0, and if you only want to look at the simpler version of it, which is sigma 1, sigma 2, then you get a square. Okay, so this one will be SUT comma SUT, the ultimate strength of the material. This will be minus SUT comma minus SUT. Since it's a square, you know what this one and this one is. So any region inside this particular domain will essentially mean that you are safe, you are not going to fail. But as you keep going, it hits this particular line and you decide that it is failing. So this is a very simple criterion in order to identify failure as far as brittle materials are concerned. It's called as a maximum normal stress theory. Now, like what I told you, what could happen, this is assuming that in tension and in compression the material behaves exactly the same way. It is quite possible that in tension the material behaves, fails at much lower values of, the values of SUT are much lower when compared to what it is in compression. So that is what is shown in slide number 27 for uneven materials. Uneven materials means the behavior in tension and the behavior in compression are quite different. So in tension it has much lower value of ultimate tensile strength. The magnitude of the ultimate tensile strength is much lower than the magnitude of the ultimate compressive strength. Now this is a very simple criterion, and this it's okay for some simple calculations, but what happens in real materials? What do real materials follow? Real materials follow slightly different criterion. They don't exactly do Rankine theory or the normal stress criterion. They follow either what is called as the Coulomb-Moore theory or the modified Coulomb-Moore theory. As far as Coulomb-Moore theory, you can take a look at it in slide number 28. So you see that it is quite different from the Rankine theory, and you have it looks more like the Tresca criterion, right? It looks more like the Tresca criterion, and it is also for the it's also for uneven materials, of course. So the Tresca criterion for uneven materials results in the Coulomb-Moore theory. So any region within this domain will basically be elastic. Anywhere if you cross the line, you are basically going to fail the material. Okay, this is a Coulomb-Moore theory, and then you have the modified Moore theory, which is what cast iron generally follows. Okay, so modified Moore theory is generally very good representation of the failure envelope for cast iron. So modified Moore theory is a slight modification. Instead of this particular line, instead of going all the way here, it stops right here. So that criteria is called as a modified Moore theory, and if you want to identify failure in the modified Moore theory, you have, so any point like I said, any point within basically is safe. Any point touching this particular line is basically causing failure of the causing failure in the material. Okay, so this brings us end. So we discussed a little bit of ductile materials at length, but brittle materials, they are anyways not only very approximate, they are not very accurate. So we just looked at the normal stress theory and the modified Moore theory. Now what we'll do is we'll just switch gears and take a look at this particular concept called as the factor of safety. Okay, so now you know theories to identify failure, ductile and brittle. Next part we'll take a look at factor of safety. What is meant by factor of safety? This is very often used in design of machine elements. Everywhere you will have to assume some factor of safety so that the design that you are coming up with is quite safe. Okay, so let us see what this factor of safety basically means. Now the example that I have put on slide number 31. So it says find the width A of a brittle bar of a square cross section under a tensile load P. So basically you have given it's a very simple problem just to illustrate a concept. So you are given a square cross section, okay, and this is A and it is subjected to some load P. The magnitude of P is known, okay. I know that this material is some copper, or say let's not say copper, I said a brittle material, so I should probably say cast iron. So it's cast iron and there is some value of ultimate tensile strength. In that particular problem I think I said yield strength, but it doesn't matter, for what I want to illustrate, I don't think that is very important at this point. So let's say it is cast iron and it has an ultimate tensile strength. We know this number is known, this P is known, okay. What we want to do is we want to find out the value of A for which this bar does not fail, for which that bar does not fail. What do we do in general? We calculate the area, we calculate the stress, P divided by A square is the stress, and we need to compare it with sigma ut, the ultimate strength of the material. This is a number, so you can find out P divided by sigma ut is equal to A square, which implies A is equal to square root of. What this means? This means that if you chose this value of A, okay, for this given loading condition, the material will fail, right? Because you have equated P by A square to sigma ut. Is that right? But you don't want it to fail. You want to make sure that the A is large enough so that the material does not fail. So what do you have to do? P divided by A square must be equal to sigma y or sigma ut divided by some value of n which is greater than 1. Okay. For example, if you do P divided by A square is equal to sigma ut divided by 1.5, okay, then you will get P times 1.5 divided by sigma ut, the whole square root, is equal to A. Now if you chose this particular value of A, then for a given P, this component will not fail, okay. So this number that you are choosing now is basically the factor of safety that is associated, that you need. It's called as the factor of safety, okay. So factor of safety generally is defined as allowable stress divided by design stress. In general, if you are talking about stress based failure of components, okay. Now this was a very simple example, right? We just had one component of stress that we were interested in order to come up with, in order to illustrate the definition of factor of safety. Now if you have von Mises yield criterion, how will you define the factor of safety? It's pretty straightforward. So the von Mises criterion says that whenever this number sigma 1 minus sigma 2 the whole square plus sigma 3 minus sigma 1, it fails, right? Now each of the sigma 1, sigma 2, sigma 3, sigma 1, sigma 2 and sigma 1 is a function of loading and geometry. Function of loading, how much of force that you are applying, and geometry also. What is the shape of the material? For example, if it was a bar, it was P divided by A square. P is loading, A square is geometrical parameter, depends on geometry and loading. So if you want to find the geometrical parameters from this equation and if you know the load, Okay, the only thing that is unknown here is the load. If you want to find, the only thing that you know is the load, and what you don't know is the geometrical parameter. So you can just write this entire expression in terms of the loading and the geometry, of which this is unknown and this is known, and you will equate it to sigma y. Again, if you equate it to sigma y, what happens? It will break, right? So you don't want it to break, so you equate it to sigma y by n, where n is a factor of safety. Usually 1.5 or 2 is taken. Definition is factor of safety is sigma y divided by uh, this function, von Mises function. F suffix Vm is von Mises function, basically this. Sometimes what happens is that you are not able to you can't find out the geometry, because this function can be quite complicated as far as the functional form is concerned. It need not be as simple as p by a square. It could be something more complicated. Under such conditions, you might not necessarily be able to find out the geometric parameters. For that, what you do, you assume certain geometry. For a given loading, you calculate this von Mises function and calculate the corresponding value of factor of safety, sigma y by FEM. If n happens to be greater than 1, then your design is safe. Okay, but usually we prefer a factor of safety close to 1.5 or 2. So that is how you define the factor of safety for von Mises criterion. For Tresca criterion, again you have a similar approach. Say for example, the what's the criterion? Modulus of sigma 1 minus sigma 3 by 2 must be equal to Sy by 2. So sigma 1 minus sigma 3 is equal to Sy. Again, if you do equal to Sy, then this geometrical, this which depends on loading and geometry, will, if you know the loading, will give you a geometry which will cause failure according to the Tresca criterion. But if you do this, where n is greater than 1, then the geometry that turns out will essentially be safe enough for the amount, for the loading that you are applying. Or you could also say calculate n by doing this. Assume geometry, take the loading, calculate sigma 1 minus sigma 3, do Sy by sigma 1 minus sigma 3. If n is greater than or equal to, if n is greater than 1, then you are basically the material is. So for modified Moore, that's a very complicated criterion, right? It had a, it looked something like the Tresca criterion. However, it had line parts. It looks something like this, right? This was the modified Moore criterion. Now, as far as this criterion is concerned, it is useful for us to have. Every time you cannot actually keep drawing a straight line, and if you want to say computationally program something and use modified Moore theory to find out whether a particular point is actually failing or not, then every time it is not possible to geometrically test. So people have done that work for you, in fact, and given you a set of factors that you can use in order to define the factor of safety. So this slide on page number 33 gives you that. So all you have to do is calculate C1, C2 and C3. Sigma 1, sigma 2 and sigma 3 are the principal stresses. SUT is the ultimate tensile strength, and SUC is the ultimate compressive strength. So you have to then, after finding C1, C2, C3, you find this sigma tilde. You find this sigma tilde, which is the max of C1, C2, C3, sigma 1, sigma 2 and sigma 3. Okay, whatever you get here, then you do SUT divided by sigma tilde will be your factor of safety. Okay, the derivation of this is given in a book called Mechanical Behavior of Materials by Norman E. Dowling. We are not going to do the derivation. By Norman E. Dowling. So if you want, you can take a look at this book, and you might find whether you can understand the derivation or not. So now we have seen this factor of safety for different conditions. So what did we see? We saw for warm mixes and for simple uniaxial loading and Tresca criterion and so on and so forth. But what is important for you to understand is that the factor of safety need not be associated only with stresses that are getting induced in the material, right? For example, if you take a long column, okay, and if it is being subjected to say a force P, okay, this is a very long column. So this area P by A, sigma compressive stress, might be less than SUC. Okay, the compressive stresses that are getting induced might actually be less than SUC. However, because of the long slender nature of this particular column, it might actually buckle, right? It might actually, how will this buckle? It will buckle something like this. It might actually buckle, right? So what you are now interested in is not the failure of the material because of stress, but the buckling. Okay, so you have to make sure that the load P is less than the critical load that causes buckling. So this also you would have studied in your mechanics of materials where they talked about Euler buckling, right? So the factor of safety against buckling will be P critical divided by P. P critical is again dependent on the geometry and the material and all that. P is basically the applied load. So you divide the two and find N. If N is greater than 1.5 or something like that, then it is safe against buckling. Okay. In a similar spirit, you can also have other factors of safety. So in a shaft, so you take a shaft and it is put in bearings and it is rotating. Okay, and on top of that, it is subject to some arbitrary forces. It is rotating. So because of some eccentric loading or anything like that, this shaft can basically start to wobble. Okay, some vibration can be induced in this particular shaft. Now the stresses might still be low, but what could happen is if the vibration or the frequency with which it is vibrating becomes equal to the natural frequency of vibration, then it will result in large deflections. Basically, it will reach a condition called resonance. Large deflections will be induced, which will basically cause the shaft to break. Okay, so in this case, stresses P by A, My by I, and stuff like that might not be important. But what is important is the factor of safety, which is associated with the frequency, the natural frequency divided by the frequency with which it is vibrating. How far is it from this? So if N is again greater than 1.5 or 2, you can basically assume that your shaft is safe. So why am I saying this? Although we have been talking about stress based criteria, the reason why I am emphasizing this is that when you are trying to design something, all these criteria also come into picture. It is not only stresses, it is also buckling, frequency, and then another example that I have given is the maximum displacement. So if you have a shaft, and it is enclosed in some box, okay, the stresses because of the loading might still be small, but you don't want the shaft to deflect outside of the box, right? In that case, the maximum deflection, the U max, okay, maximum deflection induced must be less than some known number. So U known. Okay, then the factor of safety becomes U known divided by U max. So factor of safety, while we have actually developed expressions for in terms of stress, it need not be necessary that it is always associated with stress. Other things can also come in, and that also should be kept in mind when you are trying to design a. So the factor of safety not only has to be associated with the stresses, but also with other physical phenomena that might actually be taking place in your system, and the design needs to account for that as well. But in general, at this level, we look at only stress-based design. Now, another thing that is important as when you are basically designing a component is this set of geometric um, geometric changes that occur in the particular machine element, and these are called as stress razors. Okay, so imagine, for example, if you take a shaft is not necessarily going to be uniform and solid throughout, when you are actually using it in a motor or for example in a gearbox or anywhere, right? You always need to have some sort of a hole drilled onto it in order to hold something. You need to put a ring on in order to prevent it from moving out of the bearing, and so on and so forth. So all these sudden changes in geometry which occur in the particular element will increase the level of stresses in the vicinity of that discontinuity. So let us see what I mean. So for example, if you take a flat member, if there is a hole, okay, it's fixed, and now I am applying a load P. So what happens is that somewhere here the stress distribution might more or less be uniform, but somewhere here what happens is, since the material is less here, the stress has to get redistributed. Okay, the same amount of load has to be carried by a smaller area of cross section. So what happens is that the stresses become distributed in the following manner. So if this is the hole, so here if this is the hole, the stresses get distributed something like this. They become really high in the vicinity of the hole. They are much higher than PA if A is the nominal cross section of this particular member. Okay, so this magnitude of stress that gets induced, sigma max, is what is going to be causing the failure of this component, as opposed to the nominal stresses which get induced, which gets induced not at the locations. Okay, not far away from, when compared to the P by A, what you have to worry about is this value sigma max. Okay, so how is sigma max calculated? From simply P by A, there is a factor called a stress concentration factor, KT, times the nominal stress will give you sigma max. KT times nominal stresses will give you sigma max. If it is a hole, if it is a plate, okay, a large plate with a hole, then if this is some sigma infinity which is occurring at a region very far away from the hole, then in the vicinity of these regions, the maximum stresses is approximately 3 times sigma infinity. So the stress concentration factor is basically 3. Okay, so this is the concept of stress concentration factor. So whenever you are basically comparing your local stresses that are getting induced or functions of the stresses that are getting induced, like for example the von Mises stresses, and if you are comparing it to some number, okay, like the yield strength of the material, then the stresses that you must be using are the maximum stresses that get induced in the material and not the nominal values. Okay, you need to use KT times the nominal value. In general, the nominal value by convention, it depends. I have seen different versions of this. Sometimes people use P divided by this area of cross section. Other times they use P divided by this area of cross section. So this plus this in order to define the nominal stress. So it doesn't matter, it won't make a big difference. So you should use whichever is safer. Okay, whichever is. This is called a stress concentration. Now how will you find out stress concentration factor? So for a plate with a hole, I said that the stress concentration factor was 3. Whereas for other situations, for example, if you had loading like this, it's a shaft, but now there is a groove like that. Okay, something like that. Okay, and now it is not subjected to axial load, but instead I am subjecting it to torsion, right? Subjecting it to torsion. Now when you have this sort of a situation, okay, then the stresses, the shear stresses, torsion causes shear stresses, right? The shear stresses that get induced will be higher than what it would be if these grooves were actually not there in the shaft. So if you take a look at your general textbook, the textbook that I have suggested, or your PSG design data handbook, or you can even find these graphs on the internet, they will tell you how, for example, okay, how for example, depending upon R on the x-axis, which is basically the radius of the groove, and for different values of d by r, d being this diameter and r being this radius, d by r or d by 2r, whatever it may be, okay, or some other diameter which is some other geometric parameter which is concerned with the groove, okay. For each values of d by r, they will tell you what the value of geometric stress concentration factor is. So all you have to do is you have to know what is the type of loading your member is undergoing. You have to know what is the radius of the groove, what is the radius of the shaft. So for that particular value of d by r and for that particular value of r, which is the radius of the groove, you have to go and find out what the value of the geometric stress concentration factor. This is called as the geometric stress concentration factor. Okay, so what I would like to how I would like to end this particular topic is by, if you take for example an axially loaded member, but now it has a groove. So this is A, but this is something else. This is say A by 2. Okay, this is a load P. You want to find out whether it is failing or not, right? You want to find out whether it is failing or not. You know P, you know A, you know everything. So this is a very brittle material, and you know the value of the ultimate tensile strength. So what you could do is you could calculate the nominal stresses. So I'm going to just use this area as for the nominal stress, P divided by A square times KT. So for this particular combination of loading, you can look at the data book and find out what the geometrical stress concentration factor is. Okay, so multiply that by KT, okay, and then equate it to SUT. If it so happens that this is greater than this, that means it will fail the specimen. Okay, if it is less than this, then you can find out the factor of safety N is equal to the ultimate strength divided by KT times P by A square, and if this N is greater than say 1.5 or 2, then you are basically safe. It means it will not fail, otherwise it's going to fail. Okay, so this is the way you need to use the stress concentration factor. So SUT divided by maximum stress function, maximum value of the stress function. So if it's 1 misses, you need to use the appropriate function here and substitute the values, and each of which must take into account the stress geometry. So I think with this we complete static failure theories. Now let's go on to fatigue failure theory. So right now we have been discussing about failure theories, and the general framework that is established is only under the situation that the load is stationary. It means you're just applying a load and it is fixed like that. That's it. It's not varying with time. But that is far from reality, as we all know. In general, machine components are constantly moving. Shaft is moving, gears are moving, spring may be compressing and retracting constantly. So many things could be happening, right? So fatigue failure is very important as far as design is concerned, and we need to know how we can design the particular element when it is being subjected to fatigue failure. So these are the various topics that I will look at, but let's basically consider it right from beginning. So fatigue failure occurs under repetitive loading. The key thing that we want to remember is that the magnitudes of the stresses which might be causing fatigue failure are far lower than the magnitudes of the stresses which are basically causing static failure. So that is why it is dangerous. Okay, so if you have F is a beam, F of t, so the magnitude of the stresses, so F of t, say let this be F naught sine omega t. Okay, then at any point, say for example this point, okay, this point is being subjected to tensile and compressive, right? It's being subjected to tensile and compressive because sine omega t can become negative also. So the stresses oscillate in the following manner. They are 0 and then they become maximum. The value of this stress that it reaches, the value of stress that is reached, okay, say some sigma naught, might be far lower than SUT, but still it will fail after a certain number of cycles. That is the reason why your fatigue failure needs to be taken into account. Second thing is, whenever a material or a machine element fails in fatigue, it will not show any warning. That means there won't be any local plastic deformation or anything like that. In general, fatigue failure in general will be brittle in nature and will occur because of minute flaws which start to grow as you are fluctuating the stress. As you are fluctuating the stress, the minor flaws slowly begin to grow, the cracks coalesce and fail. So you will, the surface of failure of this particular component will look as if the material has failed because of not much of plastic deformation will be there. It will catastrophically fail without any warning, because of which fatigue designing for fatigue is extremely important. This is a very important thing. Of course, the loads need not be nice and sinusoidal. They can be really random, like what can happen, for example, in the landing gear of an aircraft. Types of fatigue. Generally, fatigue is classified into two. One is the high cycle fatigue. Two is low cycle fatigue. Okay, the definitions are rather arbitrary, and for the purposes of this course in general, we assume that if the failure happens in 1000 cycles or less, it is generally termed as a low cycle fatigue, and if it is greater than that, it is high cycle fatigue. You can imagine that in low cycle fatigue, the magnitudes of the stress components will generally be high because it fails in 1000 cycles. Whereas in high cycle fatigue, the magnitudes of the stresses, the oscillating component of the stresses, like what we saw in the beam example a few minutes ago, the magnitude of the stresses will be quite low, okay, and it will take a large number of cycles to fail, much larger than 1000 cycles to fail. Again, the total number of cycles to failure can be divided into two: number of cycles necessary to initiate flaws in the particular domain or the machine element that you are given, plus the number of cycles that it takes for those initiated flaws to actually propagate and cause failure. Okay. For this, in low cycle fatigue, the stresses are so high that almost the total number of cycles to fail will be equal to the number of cycles to initiate the flaws. Okay, so it will be, the flaws will be so much that it will break. Okay, there will be hardly any time for the taken for the flaw to basically propagate and fail the system. When the stress levels are slightly low, then this component does not dominate much, and what dominates is the number of cycles to propagate the flaw. So in general, in most of the machine elements that we are concerned with, we will look at high cycle fatigue. When I say high cycle fatigue, it means that the magnitudes of the fluctuating component of the stresses, this component in general, okay, we will change that as we go along, but for now we can understand, just to have a feel for what I am saying, this component of the stresses will be low. Okay, the material already has substantial number of flaws in it because of manufacturing or whatever reasons, and the flaws are going to basically coalesce slowly and then cause the failure of the specimen. So we will be dealing with high cycle fatigue, and the number of cycles to failure in general will be much greater than, and stress based criterion is generally used to address this. So complete the types of fatigue. Now let us see what are the different kinds of loadings, how the loading can change as far as the fatigue failure is concerned. So firstly, we make a couple of assumptions in dealing with our problems. We assume that the loads are going to alternate between, they are listed in slide number 7. So they are alternating, going to alternate between a clear maximum and a clear minimum. Okay, we also will assume that the frequency with which it is doing, of course the number of cycles matter, but there is no other way the frequency is actually going to affect the failure. Okay, frequency is more means, the as long as it reaches a certain number of cycles, it is going to fail. That's all, nothing more than that. Then we also will make the assumption that a period of quiescence does nothing to the material. So basically, if you are going to apply this sort of a loading, say for one day, okay, then for another day you don't apply any loading, and then you start applying another loading, okay, then it is as if it is continuously working for 2 days. During this period, we assume that nothing is basically happening to the component, but that is not generally true. For example, if your bar is made of iron and if it is it's open to the atmosphere, and then there can be some sort of corrosion taking place during this period, and hence it can affect the fatigue life, because now we are talking about iron oxide and not iron, right? So all those things can happen. So if it is in a corrosive medium, things can change a little bit, but right now we are not talking about such things. We just want to make an assumption that if there is a period of quiescence, there will essentially not, it will not affect the specimen in any way. It will just behave as it was before. We will use sinusoidal or sawtooth waves or sawtooth signals, sawtooth stress variations with time, just for convenience. But in reality, the actual signal, the stress variation with time can be quite complicated. Okay, so we will look at only very simple systems here. There are methods for even the complicated ones, but we don't want. So what are the various situations under fatigue loading? The first thing is, as you can see in slide number 8, the first situation is fully reversed loading. So what happens in fully reversed loading? So the stresses go to reach a maximum value, reach a minimum value, reach a maximum value, reach a minimum value. The magnitudes of sigma max and sigma min are equal. So something called as the mean stress, which is the average of sigma max and sigma min, is equal to 0. So it goes from pure tension to pure compression. So this situation can happen, the beam that we just saw. Sorry, I don't think you can see that. So P naught sine omega t. So this one will cause a stress like that, with this and this being equal. This is called as fully reversed loading. Okay. After this, we can have something called as the fluctuating loading. In fluctuating loading, it's something like this. Right. In fluctuating loading, it so happens that sigma min need not even be negative. Okay, it can be even positive, and it can be oscillating in such a way that sigma max and sigma min are not equal to as far as their magnitudes are concerned. So this results in a mean stress. Okay, it results in a mean stress. Sigma mean is not equal to 0. Sigma mean is not equal to 0. Sigma max plus sigma min by 2 is not equal to 0. There will be some value of mean stress which is always present in the system. Okay. Then you have another thing that's called as the repeated loading, and repeated loading is again, there is still a mean stress except that the minimum stress that it reaches is 0, and these diagrams are clearly explained in slide number 8. So we have to understand a couple of different terminologies here. Sigma A, sigma suffix A is called as the alternating component of the stress. Okay, this is called as the alternating component of the stress. About the mean value, if you take this magnitude here, is called as the alternating component of the stress. Then you have the mean component of the stress, which we just saw. Okay, delta sigma is the range, sigma max minus sigma min. Okay, R is the stress ratio and A is the amplitude ratio. So these are the things that you need to keep in mind. You need to know the definitions of each of these terms. So now we have just introduced fatigue. Okay, but what parameter characterizes the fatigue property of a given material? So I'm going to take shaft, okay, and I'm going to continuously rotate it for a long time. Okay, some load is there, it is going to be rotating under a long time. What is the property of the material which characterizes its fatigue resistance? This becomes quite tricky, and it also is quite there is a lot of scatter in the data that people obtain as far as this is concerned. But in general, people obtain the data or the material property, the fatigue resistance of the material, through something called as the rotating beam test. Okay, the rotating beam test involves a particular they take a beam, they bend it, and then it is rotated. Okay. So what happens? This particular volume element will undergo when the beam is like this, it will undergo tension. When it goes on to the top, it will undergo compression. So right like that, this particular element of the beam, when it is being bent and then rotated, it will undergo fully reversed tension, compression, tension, compression, tension, compression. Right? It will keep undergoing that. So they will put this thing in the instrument they want to use in the Moore's apparatus, and they will keep rotating it, and they will count how many cycles it has taken for this particular material to actually fail. Okay, now that will be under a given moment or given value of loading, right? So I think I have a picture of this thing here. Yeah, so this is how it is. So there is a load here in slide number 10. So you have the load that is applied here, because of which there is a small beam here, okay, where the cursor is being pointed. So that bends, okay, and it is rotating. So for different values of loads, I get different values of different number of cycles, right? So different values of loads means what? Different values of maximum stress, alternating component of stress that gets induced. I get different number of cycles that will basically fail it. So if I have a really a large load, then a smaller number of cycles are going to fail it, and if I have really a small load, then it will run for a larger number of cycles. So they can plot this curve, okay, for different values of load. They know what stress they are basically applying. They will see how many cycles it has basically survived. Like this, they will basically plot a curve. Okay, the curve looks something like this, and this curve is called as SN curve. S is usually stress, N is the number of cycles to failure, S is generally the alternating component of stress. So if it is this, it is going to be M Y divided by I. So M is of course gives you S. So this can range from maximum moment to minimum moment. Both are equal but opposite in equal in sign, but they are acting in opposite sense. So this will give you the alternating component of stress. Okay, so it's basically the max moment minus the min moment divided by 2 into y divided by I will give, y is nothing but c. C is this, right? Distance from the neutral axis. C is this. This will give you the alternating component of stress. So M max and M min obviously depends upon the load that you are applying. Okay. For each combination of load and the number of cycles it took to fail, you can get a point. Like that, you can get different points, and you get the SN curve that characterizes this particular material. So it is believed to be a material property. So SN curves are available for different materials. So if you take a look at the curve that's right on the slide, it is plotted for aluminum. So for aluminum, you can see that on the x-axis you have the number of cycles to failure. On the y-axis, you have this the alternating component of stress which causes failure. So for one cycle, so the least value, right? The least value for one cycle, this value obviously has to be the ultimate tensile strength of the material, right? And then as you increase the number of as you expect the number of cycles to increase, you also have to decrease the number of stresses, and you see that the SN curve keeps decreasing and does not really reach any plateau or anything like that. Essentially it keeps decreasing as far as aluminum is concerned. This is the SN curve for aluminum. Now if you take a look at steel, let me show you steel first and then let me talk about other things. If you take a look at steel, it will look something like this. It will begin to decrease and then at a particular value it will mostly, there will be a knee, okay, there will be a knee, okay, and what this knee is telling you is that when your stresses that you are applying, when the stresses that you are applying, okay, is lower than this critical value, okay, is lower than this critical value, then no matter how many cycles you expose your shaft to or your material to, it will not fail at all, okay. So this critical value is referred to as the endurance limit of the material. Okay. In general, for steel you will see this knee, whereas for aluminium you will not see this knee, it will just keep going, okay. So for aluminium, how do you fix this limit? It's a little difficult. So we do some sort of hand waving and we say that, okay, let us take 500 million cycles, okay, let us take 500 million cycles and corresponding to that, whatever stress we get, we will take that to be the fatigue limit. We don't use the word endurance limit, we use the word fatigue limit because there is no clear knee like what we see for steel. Okay, so this is the difference between endurance limit and fatigue limit. Okay, and endurance limit is a stress, any stress below this particular value, if you apply, the ideally or theoretically the material is supposed to come for infinite cycles. It will never fail. See, often you don't have these numbers given to you, especially for steel. When you are trying to solve problems in your examination, no, they will not tell you what the endurance limit and the fatigue limit is. So you need to make some sort of an approximation, or you might not have the SN diagram available with you. Okay, you might have to make some approximation in order to do your problem or to get an estimate for the life of the particular component, right? So for steels, we take the endurance limit to be half the ultimate tensile strength, okay, and for aluminium, like I said, we don't take half of anything, we just look at the SN diagram for whatever the, so just the, for 5 into 10 to the power 8 cycles, whatever the value is, that is going to be the fatigue strength for aluminium. Generally we will work with steels as far as this course is concerned. Most of the problems will be based on steels only. Otherwise you will have to ask for the appropriate data. So let's take a look at the another way of looking at this SN curve. Okay, the SN curve is generally plotted on a log plot. Okay, the stress is on log base 10. The n, that is the number of cycles, is also on log base 10. And let us look at it for steel, which is actually shown in the diagram right here. On the x-axis, they have plotted thousands of cycles. So this means, if this is 1, it means 1000 cycles. And on the y-axis, they have plotted the alternating component of stress at failure as a percentage of the ultimate tensile strength. So interestingly, for 1000 cycles, okay, the stress to fail is approximately 0.9, right? 0.9, 90%. If you can see, it is 90% right here, right? And another interesting aspect is that the SN diagram on a log plot looks like a bunch of straight lines. So for 1000 cycles, the number of the stress that you have to apply in order to fail it is approximately 0.9 times SUT. So this was the alternating component of stress. This is 0.9 times SUT, and then it decreases in this particular manner as a straight line to some value, and then it becomes more or less a constant. And if you take a look at that region or the number of cycles at which it becomes a constant is around 10 to the power 6 cycles. So near 1000 to some a little more than that. So depending upon the type of steel, you can have anywhere between this and this, right? So in general, what we do is this we take to be 10 to the power 6. This value will be SE, and SE, which is the endurance limit, like I told you, if it is not given, is basically SUT times 0.5. So now this is a very simple construction which allows you to do several things. So you know this point, this you know the SUT of the material, so you can first draw the SN axis. Let us say that they are all in log plot. Okay, they are log base 10. So let us say that when this is 3, this is 3 means what? Log base 10 is 3 means this is for 1000 cycles, right? For 1000 cycles, this value is again log base 10. This value is nothing but log base 10 0.9 times SUT. Remember, this is only for steel at this point that we are talking about. Okay, so we got 1 point. Now for 6, which means million cycles, we know that it has to be the endurance limit, and the endurance limit was assumed to be 0.5 times SUT. So say this value is approximately log base 10 0.5 times the ultimate strength of the material. Okay, now after this it is just a straight line. There is nothing interesting going on there. It is just not going to fail at all. Now you join these two lines. So what do you get from this graph? What you get from this graph is, once you know this limit and this limit, it is basically a straight line. So in log graph, it's a straight line. So you know the equation of the straight line, right? You can write equations of straight line. So if you want to find out for a given value of alternating component of stress, how many cycles you can get, you just take this value, draw a straight line, and put a perpendicular right down. You will get some number between 3 and 6, say 4. Okay, if you get 4, that means for this amount of stress, total number of. So in a similar manner, if you want the component to come for say 10 to the power 5 cycles, so you will isolate a point 5, go here, figure out that you need to apply that level of stress. By simply using the equations of a straight line, you will be able to come up with the number of cycles it will take to fail if a certain amount of load is applied, or the number of amount of load that you can apply if you want the component to function for a certain number of cycles. So this is a very useful diagram, and I am sure you will be seeing it several times in your course. Remember, this diagram has at this point been drawn for a, how would I say they obtain this diagram? They obtain this diagram by this Moore's test, right? They take this beam, bend it, and then rotate it, right? So every point in the material is subjected to fully reversed bending, like that. The mean stress corresponding to this SN diagram is 0. Now we will see what happens with mean stress probably tomorrow. So this is basically the SN diagram and its use. So this whatever I said has been summarized here. So these are approximate values for the endurance limit and the fatigue limits for different materials, which are tabulated in this particular slide here. So if it is it depends on also on the whether it is 0.5 or whether it is 0.5 SUT or what it is, what the value of the endurance limit is. It depends on the value of the ultimate strength. If the ultimate strength of steel is less than 1.4 gigapascals, then you can use this half a SUT. Otherwise, you have to use other values. Okay. Now, so the endurance limit that is generally determined, or the fatigue limit that is generally determined, or the SN curve that is drawn using the Moore's apparatus, is dependent on several factors. It is not strictly a material property. Even the yield strength that you determine in the laboratory is only under laboratory conditions, right? You don't know what will happen if you take it to some cold place and pull it. Things might be different. So what is important to note is, especially when it comes to fatigue, is that this SE, the endurance limit, which you fixed to be say 0.5 times SUT for steel, is called as the theoretical endurance limit. It is the endurance limit that you get under ideal conditions. But in reality, the endurance limit might be quite different, simply because you are not exposing this machine element to to laboratory conditions, but to more real situations, harsh environments like a corrosive environment, high temperature. Okay, the surface roughness of the component that you are using in your lab in order to get the SN curve might be quite different from the surface roughness of the shaft that you have used in your gear in the actual application. Okay, all these factors play a very important role in changing and change the value of SE. In essence, they will reduce SE, that is the theoretical value of SE, by a certain amount to give you a actual SE. Okay, this endurance limit, the actual one, is obtained by multiplying several factors with the theoretical limit. All of these factors are less than 1. So the endurance limit also becomes lower than the theoretical endurance limit, and it is this value that you actually need to use when you are trying to draw the SN diagram or for other purposes. Okay, we introduced the SN diagram, I used SE, but actually you should use the should not use the theoretical one, you should use the corrected one. So let us see some of these factors which might be important. So if you take a look at slide number 17, it tells you, theoretical thumb rule prediction of fatigue endurance limits are those under ideal laboratory conditions. In reality, the components may be subject to so many external factors which reduce its fatigue or endurance limits. So we need to correct them appropriately. So the endurance limit is nothing but C load times C size times C surf times C temperature times C reliability times the theoretical endurance limit. So C load. So the laboratory in the laboratory, when you obtained the endurance limit, you basically applied a fully reversed bending load. But in reality, the component might be subjected to one axial load, right? So for that, you need to correct the endurance limit. So that is what C load is. Again, it's a value ranging between 0 and 1. So then you have C size. So you might have used a very small shaft in your laboratory, and the small materials usually have lesser flaws, so they will function very well. But in your real system, in your real when you are trying to use it for an application, the shaft might be of much larger in size and might have a large number of flaws. So you need to correct your endurance limit for that as well. Surface. So you might have a good well machined component in the laboratory, but in reality it might not be the case. So all these corrections, see temperature, reliability. When I say reliability, it means that you want a certain level of reliability. For example, you want to make sure that your the machine component that you have designed, out of 100 times it fails only 90 times, it fails 10 times. So 90% reliability. Okay. In that case, if you want to design it, you will have to reduce it even further. So C4 will basically be more closer to 0.1 or something like that. But if C reliability is very low, like out of 100 times it's okay, if 50 times if it fails, then this might be more, the C reliability might be more closer to 1. So you don't have to reduce it as much. So in this manner, depending upon several factors, you have to first correct the theoretical endurance or the theoretical fatigue limit and use the corrected one for all your. So there is a particular file, and I'm not sure if I have shared this file with you. I will do so. It contains a list of parameters which you can actually use and find out the corresponding. So this is the size factor. So like I said, one of C size is one of the factors. What it basically takes into account is the fact that in the laboratory conditions you might have used a shaft, whereas in reality you might be using a square cross section, right? All these factors can play an important role and change the value. So these are the various graphs for C surface factor, for size factor, and so on and so forth. Each of these values can simply be looked off of the table. They are very simple to use. They are not at all complicated. If you just look at the table, you will know how to use it. Now I just want to just show you a simple illustration of the SN diagram and how it can be used in order to find the life of the component. So, so it's given that a steel component is subjected to fully reversed alternating bending stress of 100 megapascal. So the sigma A is 100 megapascal. It's a steel component. Okay, it's given that it is steel component. Okay, if the ultimate tensile strength of steel is given to be 600 megapascals, okay, then the bar has square cross section with 150 mm sides and the operating temperature is 500 degrees Celsius. If it is hot rolled finish, then how do we find out the number of cycles it will take to fail? Very simple problem. So first thing is, so you have to understand that you are asked to you give the number of cycles to fail means you need the ascent diagram. Okay, you need the ascent diagram. So first draw the axis which represents the S and N. Of course, you are going to do everything in log plot. So SUT is 600 megapascals. Since SUT is 600 megapascals, for 3, that means for 1000 cycles, you can easily fix a point, and this point happens to be 0.9 times SUT. Of course, the log of this, because this is a log block plot, right? Now, you need to have another point here. Okay, you know that this point is going to occur at 6, and this value has to be the corrected endurance limit. So, if you take a look at all these factors, consider the fact that it is a square cross section, consider the fact that it is working at 500 degrees Celsius and that it is hot roll finish, they give you this, the product of all the C's happens to be 0.2332 or something like that, like what I have written down there. So the corrected endurance limit will be equal to 0.2332 times the theoretical endurance limit, and the theoretical endurance limit happens to be half SUT for steel, which is an assumption that we are making, okay, just to do some back of the envelope calculation. So the log of this will actually be used here. Okay, this is SE, this is SC, this is SE prime. SE prime means theoretical, SE means the actual. So now you know this point, you know this point. Okay, now obviously this is something like 0.9 times 600, and this one is, you know, something much lower. 100 megapascal will be somewhere here. So log base 10, 100 megapascal. For this value, you draw a straight line and drop a perpendicular. The value that you get, which is approximately 5.476. Okay, this value will then give you the number of cycles to failure for this amount of, for 100 megapascals of alternating loading. Okay, it's a very simple problem. You can do a lot more things with this. So one can also define a factor of safety for fatigue in the following manner. So if SF, so this is we have to take a look at this sentence very carefully. So if SF is a fatigue strength corrected at the required number of cycles, so at the required number of cycles, if SF is the corrected fatigue strength, okay, then the factor of safety is SF divided by sigma, where sigma is the largest component of the alternating stress which is going to occur in the particular specimen. So I have also provided an example, using the same example. A steel component has corrected endurance limit of 300 megapascal. It is designed such that the maximum alternating stress induced is 75 megapascal. Okay, so it is designed to take 75 megapascal. If it is to work for 3 into 10 to the power 5 cycles, then how do we calculate the factor of safety? There is nothing but 100 divided by 75. So 100 is the, from previous problem we know that the fatigue strength for 100 megapascal was 3 into 10 to the power 5 cycles, right? Was 3 into 10 to the power 5 cycles. So for 75 megapascal only I am applying me, what will be the factor of safety? It's going to be 100 megapascals divided by 75 megapascals. So this is the way we can actually deal with ascent diagram. Okay, so we have completed basics of fatigue where we talk about ascent diagram, and ascent diagram was actually independent of your mean stress. In the next class, we will talk a little bit about how the effects of mean stress are actually going to play an important role, and then we will conclude that, and how do we design components with that, and then decide on factor of safety. and then we will go on to probably deal with a little bit of fracture mechanics if we have. With that, I'd like to conclude it, and if you have any questions, you can. Yes, somebody has a question. KSRCT.
In the SN curve, why we are taking x-axis and y-axis in logarithm form?
See, the reason is it is because for steel specifically, if you happen to take the x-axis and the y-axis in log scale, then the SN curve becomes a system of straight lines. So you know the equation of a straight line. Given 2 points, you can draw a straight line. Once you know what a straight line, once you know the straight line equation, you can arbitrarily find out for any given alternating component of stress, you will be able to find out the corresponding value of life. So it is only for that purpose that we can use the log plots, because it looks like a straight line. The SN curve, if you plot it in non-log plots, it doesn't look like a straight line and you don't know how to work with it. But when you plot it on log graph, it looks like a straight line. Endurance limit, to the best of my knowledge, endurance limit is calculated based on the Moore's apparatus test that I was talking about. That is one way I know they calculate it, but I am really not familiar with the ASTM standard that is used in order to fix endurance limit. So I don't know. Please give some examples of reversed fluctuating stresses. So when you ask for examples, I'm not sure, like it could be occurring under different conditions. So if you take this here, so let us take a shaft. Okay, on top of it we attach some sort of a gear. It is connected to another gear. Just a simple cartoon. Now you know that there are forces between this and this, right? So there's going to be some sort of a radial force, some sort of a tangential force that is acting on the gear, and these forces are going to get shifted onto the shaft. So as the shaft is rotating, in addition to that, it is also being subject to some sort of bending force, right? So this is an example of fully reversed bending as far as shaft is. If the load from the gear is basically going to is fixed, it's not varying, and there can be many, as long as your stresses are changing from the same positive value to the same negative value, it's fully reversed. Y alternating stress component is half the difference between maximum and minimum stress. That is the definition. That's it. It is basically this amount. So from the mean value, whatever is this is the alternating component. So so that is the definition. So I don't know what else to say. So sigma max minus sigma min by 2. So if there is a mean stress, so this is 0. If there is a mean stress, then this would be the alternating component. What is exactly the von Mises stress which is used in design software for analysis? Von Mises stress is only one thing. Okay, so there is no separate von Mises stress for softwares and separate von Mises stress for other applications. This function that you see here is the von Mises stress. Why static stress concentration factor is more than fatigue stress concentration factor? This is because of a reason that we will see tomorrow, because the material has something called as notch sensitivity. Since some of the materials will not be sensitive to the presence of the notch, especially under fatigue conditions. For this reason, the fatigue stress concentration factor becomes a little lower than the static stress concentration factor. What happens to the factor of safety when stress concentration factor increases or decreases? See, when stress concentration factor increases for a given loading, the factor of safety decreases. Okay, when stress concentration factor decreases, see, you have to think about why you are asking this question, because when you say stress concentration factor is decreasing, are you meaning you are like changing the geometry so that it is more smooth? If that is what you mean, if the stress rises are basically going away, that means that the factor of safety will increase for the same loading that you have. Real application of reversed alternating stress. What is real application? So the alternating, any shaft with a gear is a real application with a fully reversed stress, and it has an alternating component of stress. So I'm not sure. There can be many applications. I can't like list them at this point. I don't know. Sir, can we call alternating component of stress amplitude stress? Yes. Call amplitude of the stress. Yes.
Hello.
Hello, sir.
Hello, sir.
Sir.
From GCT, Coimbatore,
Yes.
sir. Sir, can you say about design for finite life and design for infinite life?
We will talk about it in the next class. I will cover it in the
Next class. Okay. Thank you, bros.
Modified Mohr Coulomb generally is used for cast iron, but it could depend. Okay, which question is which theory is best suitable for brittle material and why? See, there is no uniformly applicable theory for all the brittle materials. Just like how there is no uniformly applicable theory for all ductile materials. You have to try it out. So for cast iron, people have shown that the modified Mohr theory is good because experiments and the theory basically match well. But otherwise, it is only used to estimate the failure, and it can depend from material to material. I would suggest a modified Mohr Coulomb, and because for cast iron it seems to do well, and we are hoping that it will do well for the other. What happens to factor of safety? This I think I answered. There are no other questions. I'd like to stop. Thank you very much.